Hello, and welcome back. In this video, we're working through an example of two-dimensional motion in a gravitational field. So this is a follow-up of the last video where we worked out some general equations under the assumptions that the only force acting on our object is gravity, and with initial velocity u naught v naught and initial position x naught y naught. And we recovered these equations for position and for velocity. So let's, so what's the plan here? We have a few things that I want to do. I want to start by showing that the trajectory is parabolic. Now, we've probably heard this before or noticed this, that an object sort of launched and then allowed just gravity to act on it will follow a parabolic trajectory. So what does this really mean, and how can we show that this is in fact true under these assumptions? That's our first step. Step number two is I want to find these things: range, max height, and time in flight. So range is how far the object goes after it's launched. Max height is straightforward, right? What's the highest height that the object achieves? And then lastly, I want how long does the object stay in the air? So that's step two, is find these quantities. And then step three, we have a special question here. Does the ball clear a 20-foot fence that is 380 feet from home plate? Okay, so if you would like to try and work this out on your own, any of these steps, maybe one, maybe you don't want to do that one, that's fine. If you can do two or three, go for it, or just make an attempt on it. I think the learning process is a lot better if you kind of just try it first, and then if you get stumped, you can watch someone else kind of work through it. That's the goal of this video, is to be that guide to help you work through it if you get stumped. So let's go ahead and start with showing the trajectory is parabolic. So what does this really mean? That means if we plot this, so if I have my y-axis here and my x-axis here, so think back to Calc 1. A lot of times we put, say, height. This was like our height axis, and this was like our time axis. And we tracked how high the object was after a certain amount of time, and that was parabolic. But that's not, doesn't describe the trajectory of the object. This is height compared to time. This isn't what the object actually looks like as it moves through the air, right? It's just tracking how high it is over time. So we don't want to think about it like that. When I think about trajectory, I want to think about if I actually see this object moving. So if I'm facing the plane in which the object is moving, and I let this be the x direction and this be the y direction, I want to see the parabola here when I graph it on these set of axes, x versus y. That's the idea. So how do we show this? Well, I want to show that, so what does parabolic mean? That means it's a quadratic function of x. So I want to show, let's say WTS, want to show that y is a quadratic function of x. So how do I do that? Well, I better start by just getting my velocity and position, right? So this is x compared to y. If I have my position function, right, r of t, that has both the x and y components in it, then I can take those and hopefully show this. So first step, let's go ahead and get a hold of position and velocity equation. So, all right, so what's my initial velocity? 80, 80. Very nice. Initial velocity. What's my initial position? What's my r naught? Well, for that I have to read a little bit. Baseball's hit from 3 feet above home plate. So let's go ahead and let our axes be such that home plate is here at x equals 0. So let's say this is home plate right here at the origin of my axes. That seems to be fair. And then we're hit from 3 feet above home plate. So that means my x component should be 0, and my y component should be 3 feet. This, unless I want to convert everything here to meters and meters per second, I better work with feet in this, because my velocity is also in feet per second. So that means my g is going to be minus 32 here. Not minus, rather, but just 32 feet per second squared here. So we're using, feet per second squared for our gravity. Okay, so let's go ahead and work out what our equations look like. So v naught, or sorry, v of t, should be, right, again, ways to remember this is my velocity. Maybe I'll start with acceleration, actually. Let's start with acceleration. Let's just refresh our memory. So what's the acceleration on this? Well, there's nothing happening in the x direction. It's all happening downward in the y direction, so this is minus 32 here. Minus g, and g is 32. So that means my velocity, v of t, will be my initial velocity in the x direction. That's my u naught, as I've called it. That's 80. And then in the y direction, it's also 80, and then I'll have a minus 32t here. Minus 32t plus 80. Now, I'm just kind of piecing through this myself, just remembering what the formulas are. Don't be afraid to jump up to these formulas that we already derived or rederive them. So that's where I'm getting all of our velocity function from and our position function from, is from this derivation from the previous video. So if you haven't watched that yet, it's a good idea to do that to see where I'm getting these things from and how I'm remembering them. And then lastly, we have our position. So we'll start with 0 in the x direction, right? So I should just have 80t here. And then I'll have minus 16t squared, derivative there, plus 80t. And then I started 3 feet above home plate. That's the idea. So I want to show that this, my first goal, right, is to show this trajectory is parabolic. So here is my y of t, and here is my x of t. What I'd like to do is I'd like to compare y to x. I want to see y as a function for x. So in order to do that, I'm going to solve this for t, right? So if I have x equal 80t, that tells me that x over 80 is equal to t. So now I have t as a function of x, and then I can evaluate y of t, or y of x over 80. So then y of t, which is the same thing as y of x over 80, looks like minus 16 x squared over 80 squared plus 80t, so that's 80 times x over 80. Oh, that's just x. That's cool. And then finally plus 3. Okay, so we could simplify this a little bit. That's fine, but we don't really need to, because now I have y as a function of x. So my y component as a function of the x component, we have that function now. It's minus 16 over 80 squared, x plus 3, which is quadratic, and forms a parabolic trajectory. So parabolic, wow, having a little bit of trouble writing. Parabolic trajectory. Cool. Next thing I want to get a hold of are these things: range, max height, and time in flight. So, right, maybe I'll draw on my axes just to kind of describe this again. So here is my my y component. Here's my x component. My trajectory looks parabolic like this. What I want to get a hold of here is, well, one, the range, which is this x value. So this is my range. Where does it hit the ground? My time in flight, t. So I'm going to let t equal time in flight. So that's how much time it takes to get from this point here to that point there. I can't really draw it on this graph because time isn't pictured here. I want the amount of time it takes to get from here to there. And then lastly, I want max height. So if we think of range like maximum distance traveled in the x direction, max height is the maximum in the y direction. All right, so how do I get a hold of these things? It turns out getting a hold of time in flight may be the best way to start this. So let's try that. So how do we find time in flight? Well, what happens when I hit the ground? What's going on here? What do I know about my function there? I know at this point, I don't know what the t value is. I don't know what the x value is, right? That's the range. And I'm trying to find the t value, but I do know the y value, right? At this point in time, I know the y value is 0. So I know that y of t is equal to 0. That's how I'm going to get a hold of the time in flight. Now, again, we've encountered this likely before in, say, a Calc 1 class. We should get 2 points where my y component is 0. It's going to happen over here and over here. In this case, with our graph drawn like this should happen for a negative t value. So we're going to want to throw that out and pick the positive t value. So let's go ahead and figure this out. We have y of t. Let's jump up. We had y of t. There it is. There's y of t. So let's go ahead and find when y of t is equal to 0. So I'll write this down here. Y of t equal to 0 implies that minus 16. Notice I'm using a big capital T here as a constant for time in flight. Plus 80t plus 3 equal to 0. So now we have a quadratic equation to solve. We could do this either using a graphing calculator. We could use this with the quadratic formula. Pick your favorite way to solve a quadratic, and let's do it. All right, so if you haven't yet, find the solutions to this. I'm going to just use Wolfram Alpha, which is a free online calculator that you can use if you don't have, say, a TI-84 or a graphing calculator of your own. You can use Wolfram Alpha. I absolutely condone that. And let's see, I maybe should zoom in a little bit here. All I did was plug in minus 16x squared plus 80x plus 3. So remember that, I mean, I could have put t in here for my variable. It's not going to change what comes out. All right, assuming t is a variable. Yes, yep, that's right. I do want to verify that. And then here's my function. And this will just tell us exactly what our roots are. I'm going to look at approximate forms for these roots. So we get negative 0.037. That's the one I want to throw out. But the 5.0372, I want to keep that one. So I'm going to round this to 5.04 and use that number. Again, you could use the quadratic formula. You'll end up with the exact forms for these roots. That's great. Or using graphing calculator, maybe using the graphing function and then finding the intercepts. You can get an approximation. So I'll use 5.04 for this. However you want to find those roots is up to you. So t, my time in flight, is 5.04 seconds. Cool. So that's my time in flight. That was one of the big three I wanted to get a hold of. And that's going to help me get a hold of the range. Because this is the point that I'm really interested in for time in flight and for range, right? This is when I hit the ground again. So the amount of time it takes, that's the 5.04 seconds. And then whatever the x value is here, that's my range. So that is range is x of big T, my time in flight. So for that, I'm going to look at my x component. It's 80t. So this is 80 times 5.04. And that gives me, about 400. Let me grab my calculator real quick. Let's get it exactly. So I have 80 times 5.04. I get 403.2. And that's in feet, because my velocity and acceleration were all in feet per second and feet per second squared. So that's my range. Cool. How do I get a hold of max height? You might be tempted to say, oh, the max height should occur in the middle of this parabolic trajectory. And you'd be right, but you'd have to factor in this part of the parabolic trajectory before the baseball is hit, and then find the middle between the two roots. We didn't keep track of this other root. I guess we could go back and add it to this root. We'd have, 5 point something and divide that by 2. We could go that way, but that's also based on an assumption that the max height has to occur halfway in the middle. I mean, we'd be right for this particular example, but we want to be able to do this even if there's other forces going on. So how do I locate the max height? Well, what I can do is I can figure out what my derivative is, the derivative of my y component, with respect to time. Right, if I'm just looking at derivative of y component with respect to time, when that goes to 0, that'll be when I'm at the max height. So I really want to consider when is dy dt 0. So I'm going to say here max height. This occurs, I don't need two s's there, occurs when dy dt, or y prime of t, is equal to 0. So y of t, we have that. That's this one. So that's minus 32t. Or we can think of this like this is v of t, right? Not v of t because we don't want the full thing, but the y component of v of t. And that was, so this was minus 32t plus 80. So we'll go ahead and solve this, right? We have 0 equal minus 32t plus 80. This is particularly nice example. We get t equals exactly 2.5 seconds. So that's cool. Notice it's not exactly half of our time in flight. And again, that's because of this discrepancy, because we're not starting from 0 height. We're just looking at part of the parabolic trajectory. So if we made that assumption, we could be off in a significant way. So this is good. That is, right, so that's the time at which we achieve max height. So let me say here, this is the time when max height is achieved. So that means if I take y of 2.5, that'll tell me the max height, right? That's my y value at the time when the max height is achieved. So y of t. Remember, don't use the y of x. I really just used y of x for showing it was a parabolic trajectory. That's y in terms of x. We want y in terms of t. So plug 2.5 in for t there. So this is minus 16 times 2.5 squared plus 80 times 2.5 plus 3. Let's go ahead and calculate that. By the way, I'm just using a TI-30X2. Use whatever you have. Use Wolfram Alpha. I don't care, as long as you are comfortable with whatever you're using. And if you're not comfortable, that's a point where you can come and see me. If you're not able to do these things with your technology, you can come and talk to me, and I'll try and help you out. 2.5, I'm just entering that again, minus 2.5 squared times minus 16, minus 100, interesting, plus 80 times 2.5, 100 plus 3, so we get 103. And that's feet. And this is my max height. So there we have it. Right, and this is kind of the beauty of it. So given that initial velocity, that initial position, we're able to work out a lot of these key characteristics of the trajectory, right? How much time does it take before it hits the ground? How far does it travel horizontally? What's the highest, y component? What's the highest height that it achieves? These sorts of things. So we can also do extra stuff with this. So I'll return to part 3 here. Does the ball clear a 20-foot fence that is 380 feet from home plate? So how do we solve this one? I want you to think about this for a second. How can we solve this problem? What sort of information can we synthesize and then use to our advantage? So let's kind of talk through how my methodology here. So does the ball clear a 20-foot fence? So this is really asking, is the height of the object high enough, right? So is y bigger than or equal to 20 feet? And at what point? Well, the point is when the x component is 380 feet. So if I say, let's say t naught, let's define t naught such that x of t naught is equal to 380. So if we're able to get a hold of the time when my x component of my position is 380 feet, then I can take that time and evaluate it for my y function. Then check if y of t naught is greater than or equal to 20 feet. Greater than or equal to or greater than. If it's exactly 20, we have to sort of think about whether or not it clears it or not. We might have to investigate what's the diameter of the baseball at that point. So hopefully we see that it's not right on the edge. If it's right on the edge, we'll have a discussion. So let's check. Let's see. So right, I want to figure out this t naught first. So this almost mirrors what we did here. We found time in flight first, but that was with y. And then we plugged that into x to find range. So it's kind of mirroring that same process, just with different equations. So let's go ahead and set this up. I want x of t naught to equal 380. So this is, we're saying part 3. So when, I'm going to say x of t naught is equal to 380. What's my x, my position again? I can scroll up here and find, right, this is the idea, is it's all conveniently located inside my position vector. So 80t is my x of t. So that's 80 t naught equal to 380. I can now easily find t naught. So that's 380 divided by 80. I get t naught is 4.75. Cool. What now? Now, again, I want to test whether y of t naught is greater than 20 or not. So now, what is y of t naught? So that's y. Now that I know what t naught is, I can say, what's y of 4.75? I'm really having an issue writing in this video. 4.75. And so that's what? Minus 16, 4.75 squared plus 80 times 4.75. And then plus 3 was my y equation. Let's go ahead and plug that in, see what we get. I hope you're doing this along with me. I really advise you pick up your calculator, find it, pause the video if you don't have your calculator in your hands. Figure this out with me. That's sort of the best way of learning, because again, one skill is being able to use the technology around you to, say, do arithmetic like we're doing here. So we got to be able to do that. And so I want you to practice along with me. That way, if you make a mistake, you can tell and try and correct yourself. So what do I get here? Y of t naught is 22 feet. And that is, right, 22 is strictly greater than 20. And so, yes, the ball clears the fence. Isn't math cool? I think so. Right, we started with just a question: does this ball clear this fence with these parameters? And we're able to work through using our vector equation and be able to figure out an answer. Yes, it does. Very cool. Okay, so that's it for this video. Remember, we were just working in 2 dimensions here. What happens if we add a third component to these equations? So if we have, say, a horizontal component, a left-right component, maybe there's like some spin on the baseball that's causing it to accelerate either left or right. And then we also have our z component, which is where we're going to stick gravity. So we're sort of expanding this first component. Our lateral component now is going to be 2 dimensions. This will remain similar. So more on that in a later video. I'll see you there.